Masterclass is on sizing cold rooms and equipment selection. So as we go through, we're going to look at very fundamentals of heat transfer. Just as a recap, it's not going to be anything in depth at that point. Hopefully most people here are familiar with it, but some of the terminology might be useful as a refresher. Moving on to the heat loads of what we actually need to calculate for example, a cold room. We have four aspects. We have the fabric loads, product loads, infiltration loads, and ancillary loads, which are effectively anything which doesn't fall into the first three categories. From there, that's where the majority of our time is going to be spent today, but then we're going to look at some equipment selections as well. So we'll have an example of an evaporator selection, our compressor selections, condenser selection, and then alongside that, if you're just selecting a condensing unit, we'll look at how to do that easily as well. And then at the very end, a quick summary. So diving into heat transfer fundamentals, heat transfers through one of three ways generally, or a collection of all three. So we have conduction. If I physically put my hand on my water bottle, the heat from my hand will transfer into the surface of that bottle, that plastic, and then it will pass through into the water. That's conduction. Convection would be once that heat transfers through into that fluid inside, whether it's water or on the slide, a cup of tea or coffee, the molecules inside will become hotter at the outsides where it's first transferred into, and then that fluid will transfer, each of those molecules will hit into the next ones, and it'll start to warm up the rest of the cup. And then radiation, which isn't generally too concerning to us in terms of how we manage our heat. We don't have very high emitting or high radiation emitting heat loads, and particularly in retail cold rooms. But for example, if you had radiant panels in a large warehouse, for example, for heating, for spot heating in winter, that emits radiation, and that is heat which transfers through no medium. So all the heat that the Earth experiences from the sun is transmitted as radiation through the vacuum of space. Majority of the heat transfer we rely on and try and counteract in refrigeration will be conduction and convection. All well and good. It's not particularly useful to us, I think, but things we do need to know is that hot goes to cold. It doesn't tend to go the other way around. While in refrigeration, we need to make things cold whilst it's hot. Yeah, we have to try and cheat the laws of physics. So we need to find some sort of mechanical process, which majority we use is the vapor compression cycle. But we need to know if we make a space colder, heat is going to try and get into that space and warm it back up again. And the more difference there is between hot and cold, the faster that process will happen as well. And we measure this heat through various methods. So we have our temperature scale in Celsius, Fahrenheit. If you want to be scientific, use Kelvin, or if we use imperial measurements, it's Rankine. We're going to use Celsius and Kelvin today. And each step change between Celsius, so 1 degree Celsius to 2 degrees Celsius, is the same as going from Kelvin. The scale just starts at a different point. So Celsius, 0 Celsius is the freezing point of water at sea level. In Kelvin, that's 278.5 Kelvin. So I should know that off the top of my head, but I don't, I'm afraid. So diving into it, we're going to look at trying to calculate the heat load to be removed from a cold room today. So only a small room as our example later on, but this scales up to any size. So first off, we have what we call fabric loads. So that's any heat that comes through the walls, floor, or roof of a space. In addition to that, we have our product loads. So what do we actually want to cool within that space? Generally a pallet of food or a cage of milk. Instead of being a cold room, if you're cooling a process inside, that would be the same as well. Infiltration load, so that is the air that enters the space. So air outside is normally warmer and more moist than the room air inside the cold room, so it's going to add heat to that space when the door opens. We need to take that out as well. And then ancillary loads, so that is, for example, any people who work inside the room or enter it, lighting. We also have our evaporator loads there. We have our evaporator fans and our defrost heaters. And then you also may have machinery inside as well. If it's a large cold store space, you might have forklift trucks operating, conveyor belts, etc. And then all we do is add all these loads together And that gives us our total cooling load. And we're going to use kilowatts today. We're not going to use BTUs, tons of refrigeration or horsepower for selecting compressors. My brain doesn't work like that. We're going to use scientific units here. So apologies to anyone who does select equipment based on that. You can do the conversions maybe in your own time. So just to baffle everyone who's not done an engineering course here, we have some scientific notation we need to look at and refer back to at times. I've tried my best to try and fit the explanations of these onto each slide, but as you can see, there's a lot, and it would run out of actual space on the screen. The main ones I wanted to just go through before we move into it is, if I get the laser pointer active, we have this value down here, or this symbol, which is sigma, and all that indicates is that we add up every type of that sum. So if we're adding up all the fabric loads for a room, we'd calculate each wall or surface individually, add them all up, and then that gives us our total fabric load in that space. We have Q, and that is just our heat load for the space. So we're going to use kilowatts. And then we have some other symbols here, which people should be familiar with. So delta T and delta W. Delta T is our temperature difference, which is our sensible temperature, and delta W will be our change in moisture content in the air when we get to latent heat loads later on. So we'll dive straight into fabric loads. So these are what loads are transmitted through the surfaces of the room. So our walls, floor, ceiling. Generally, a space will have at least 6 surfaces. More advanced or complicated rooms may have more. And again, you'll have to do this calculation for each surface. If part of a room is up against, say, if you have a chiller room and we have a freezer room on one side, the temperature difference will differ versus if it was exposed to an ambient temperature or if it's outside, with sunlight hitting onto it. So you do need to take this into account and look at as a site-specific consideration. So what do we have here? So the 3 things which we'll have is the thickness of the surface, how well that material of the surface conducts or resists heat transfer, and the heat differential across the 2 sides of the surface. So when we look at these values on the left-hand side, we have our material thickness, and then we have our transmittance, which is effectively how insulating or how poorly insulating that surface will be. A typical cold room panel of 100 millimeters thick would be roughly 0.18 watts per meter squared per Kelvin. So if we only had 1 meter squared and we had a 1K difference, so say it was 20 degrees inside the room and it was 21 outside the room, we'd have 1 Kelvin across 1 meter squared. That'd be 1 watt for that area. Well, we don't tend to get that. So we need to figure out what's the surface area of each of our surfaces, our walls, for example, know what the material is, and then know our temperature difference. So our temperature difference, so any room we do, will be the outside condition at its worst case. So if we're in a warehouse, if we're in a fairly airy warehouse, back of house area for a supermarket, for example, you may only get a temperature maximum of 25 degrees there. If it's a very, very warm space or air builds up or machinery is kicking heat into that area as well, it might be 32 degrees. Our inside temperature is going to be our design condition. So for a chiller room, for example, normally 1 degree Celsius. For a freezer room, minus 21 is typically an industry standard there. Our temperature difference will be that outside condition minus our inside condition. So 25 degrees in a warehouse, 1 degree inside the room, 25 minus 1, we have a 24K delta T across that surface. To calculate the surface area, we go for width times the height for walls. Our ceiling and our floor will be the length times the width. Depending on material type and material thickness, we'll have different U values, which is our transmittance for it. So for a typical cold store, if we have 100 mil thick panels on the walls and ceiling, they'll all have the same U value. But the floor may be different because you'll have not only, you might have concrete, you may have a slightly larger or slightly smaller base to it. All these things need to be taken into account. So you need to look at on a site-specific condition. And then once we've done all this, our heat load. So at the very bottom here, we have QF. So I'll just put as our heat load, Q. I'll put F for fabric is equal to sigma. So the sum of everything in brackets, our U value, multiplied by our area, multiplied by our temperature difference. And all that means is we add it. We do that U value times A times delta T for every individual surface, add them up. And here's what may throw people. That value, it calculates in watts, because we have transmittance in watts per meter squared Kelvin. To get to kilowatts, which is what we tend to select our equipment as, we need to divide that by 1,000. Nice and simple. Fabric load should be the most straightforward one to calculate. You can get some odd-shaped rooms and some differences in fabric loads, and do you have panes of glass in it as well? All these things taken into consideration. And this doesn't just work for cold rooms. This would also be the same with air conditioning systems. But with air conditioning, you often have to take into account solar gains through glazing as well.